Okay, well, that's just about time to start the afternoon session. So, good afternoon to you, and welcome to the standalone session. I'm Neil Duncan, and I'm part of the technology team at the Oil and Gas Authority in Aberdeen. And I'm tasked today with keeping the programme to schedule, and our rather enthusiastic presenters here in the front row in check, because I know these guys quite well, and they could probably talk for hours and hours about their individual technologies, but we've kind of limited them. Yes, you're good. Limited them to about 30 minutes each. Yeah. Before we get started, just for your comfort and safety, I just need to run through the fire evacuation stuff that you've seen earlier on, so I'll try and keep that as brief as I can. Exits, there's one at the front here, there's one at the back. The one at the back leads downstairs and essentially just muster in the car park 2 area. As previously, if you just keep your mobile phones off if you could, it'd be much appreciated. Now, today's session is all about standalone technology, so I guess the first thing is to understand, well, what do we mean by standalone? Well, these are solutions that can produce, process, store and offload hydrocarbons. It's essentially oil and condensate that we're talking about today. Now, they don't have any reliance on existing platforms or existing pipelines, so these are true standalone technologies, perhaps a little bit disruptive in nature, but that's not necessarily a bad thing. Now, standalone facilities are not new. For instance, most of you will be familiar with the traditional FPSO that we all know and sort of love to different degrees, I guess. There's a significant number within the UKCS and also worldwide. However, you know, they do have some disadvantages. Some tend to be kind of large. In many cases, they're inefficient, quite costly to maintain, and also to operate. Quite often, they're converted vessels rather than being purpose built. Tend to be oversized, quite often underutilised for the given application, and quite a lot of them are reaching, or already have reached the end of their design life or their economic life. So all these factors can result in high OPEX, low availability, which all adds to the cost, can result in early COP for some of our fields. Obviously that's not good for maximising economic recovery from the UKCS. So as such, they may not offer a viable field development solution for many of our undeveloped discoveries, which tend to be quite small and certainly marginal in nature. Today you'll be hearing from 3 different solution providers, all active in the standalone arena, and they all offer alternatives to a traditional FPSO. Each presenter will introduce their technology, what it does, and how it might benefit traditional solutions, and in particular how applicable it is to the UKCS. We've also set them a challenge to investigate a couple of real-life scenarios that we put to the guys on some clusters that we were aware of within the central North Sea that might be quite a good fit for some of these technologies. We'll also hear about how they got on with those findings in the presentations that follow. So what does the programme look like this afternoon? Well, first we'll have SeaCaptaur, and Bill Thomson will tell you about their unmanned subsea storage tank and compliant spar-based production system. We'll then hear from Ian Herd of Amplis, and he'll tell you about their versatile production unit, which is a highly mobile, dynamically positioned small-scale production system with a quick disconnect facility. We'll then have a 30-minute break, so feel free to grab some refreshments and make use of the exhibition area. We'll have about 30 minutes, hopefully, if we maintain the schedule. After the break, Steve Williams of NOV will tell you all about their rather cutely named Honeybee small-scale FPSO system. And then we'll have a 20-minute break just for a 20-minute Q&A session. And that panel will be made up by the speakers, so you'll maybe have your questions ready for these guys. I'd just like to re-emphasise that we've got 36 technology exhibitors across the various themes today, and those areas will remain open till 6:30. So there's plenty of opportunities for further networking. If you want to make use of that, would be much appreciated. So any questions you have, if you can leave those to the end of the final presentation, we'll then invite the panel up to hopefully answer any questions you might have. So I think that's my time just about up. So I'd like to introduce first speaker, who will be Bill Thomson, SeaCaptaur. Now Bill has an honours degree in mechanical engineering. He's worked Diamond Power, Babcock Energy, Hunting Oilfield Services in various roles, including operations director and commercial director. He was responsible for the development of Clyde Blowers, worked in China for 23 years. He's also chairman of Clyde Blowers entities in China and India. And he also was awarded an OBE for his services to industry. He's a master's degree from London Metropolitan University. He's also a visiting professor at Strathclyde University. Since retiring from Clyde Blowers in 2015, Bill's been working on several projects, assisting UK companies entering the Chinese market and overseas. He started his own company, Sino-Scott, May 2016, and joined the board of SeaCaptaur in July 2016, and became managing director to lead their efforts in the UKCS. So that's quite some introduction, I think. So I'd like to invite Bill up to give his presentation on the SeaCaptaur system. Thanks, Bill.
Thanks very much, Ian. That was a great introduction. Okay, here we go. Well, good afternoon, ladies and gentlemen. I was going to give a little introduction myself, but no need after that tremendous introduction, so we'll just get down to business. As Neil said, we're going to be talking about standalone solutions for hubs and clusters and to unlock marginal developments. This is what we've been working on for quite a while. I'll give you a brief overview of the SeaCaptaur technology, and then look at our economic models that we've been working on for quite a while, and then give you a brief introduction to the OGTC design premise, but I'm assuming there's quite a lot of people in the room have got some knowledge of that at least, and then the cluster analysis itself, and some conclusions that we have drawn. So the SeaCaptaur system is pretty simple, really. It consists of a subsea tank, 65,000 barrels capacity is our standard size, but that can be modified depending on the situation, and a production spar, which has got the processing facility in the top section of the spar, and a shuttle tanker to offtake the oil. So as I say, it's quite simple, and it's quite small. The tank, it's not that small when you see it next to a man, right enough, but that's a standard tank. The reason we want to keep it around the 65,000 mark is because we can launch the tank and deploy it using a large anchor handling tug rather than a heavy lift vessel, which tries to keep the cost down a bit. I think for small fields, it's all about trying to keep the cost down. So the tank, I should say that we've got already 4 patents that have been granted for various parts of the system, the tank being one of them. So this is the world's first double-walled MARPOL compliant tank. So the seabed location simplifies the architecture and reduces the met ocean forces. There's a lot of development been going on in the wind industry recently that's helped a lot with the development of some aspects of SeaCaptaur, like the piling systems that are being used on the new types of supports for offshore wind. So these things also help to keep the cost down. The tank, although we have processing in the spar, the tank also acts as a secondary oil water separator, and it's connected to the spar via the riser flex joint. I would also just like to say that this tank, we've had a lot of work done on it. We used a company in Perth called GHD, and you know, there's a lot of work has already gone into this. The spar, I'm sure you've all know quite a lot about spars. I mean, it's not new technology, it's been around for quite a long while. I was reading a paper recently produced by a company called Mies Doris, who are using spars now for supporting offshore wind turbines, call it AWC, articulated wind column, in water depths of 50 to 200 metres. But of course there was many spars in the North Sea and elsewhere around the world before that, going all the way back to projects like Maureen, which was first commissioned in 1982 and operated successfully for 18 years. And I think there's about 13 spars have operated in the North Sea with several hundred years operating experience between them. We have had a lot of work done in this spar to make sure it will stand up there. First of all, we used a bit of a guru in the analysis of structures like this, a guy called Kent B. Davies in the US. And after Kent had done his stuff, we also had Intech C do a proof of concept on the whole thing, so that included the spar and the tank. So the spar here, the idea is that it will be normally unmanned. There's a full SCADA control system in there with communications to shore and to the chase boat, and we would only put personnel on board for regular maintenance or breakdowns, but we would hope that because of the simplicity of the process, that would be minimal. Now, what would be the ideal standalone field? I think it's a bit obvious to say no production infrastructure close by. That's what we're talking about. I think in Carlo's introduction this morning, he was talking about the 363 unsanctioned fields in the UKCS, and there's about 125 that are so-called standalone, more than 20 kilometres away from a facility. 10 to 30 million barrels recoverable in water depths of 80 to 300 metres. Of course, we would like to start with something maybe about 150 metres. A relatively low gas-oil ratio. We don't really want to have too much gas, although we do have use for the gas. I'll talk about that in a minute. We've modelled lots of different crudes in the system from around the world, from about a 20 up to a 55 API, and we would also like a lower risk reservoir to start with, that's got there's good knowledge of the reservoir. Maybe there's been an extended well test, or there's crude samples available, and you know, really a very clear idea of what the recoverable reserves are going to be. Recoverable reserves could drop to 5 million in a cluster development, and that's really what I'm going to come on and talk about. Give you a brief introduction to our model. I've been working with my colleagues Ian and David here on this for almost a year now. The inputs on the left hand side are only a few examples. There's many inputs to this model. It's become quite sophisticated as we developed it for different purposes. This cluster study is only the latest purpose, and we've been refining it as we go. The right hand side is showing the typical outputs, And what we've come to understand from working on lots and lots of different variations of the model is what are the key drivers and constraints to these to the model. The graphic at the bottom is just once something we've developed to let you see a picture of what happens, and it's showing the individual field revenues as the coloured bars, and the cluster revenue is the largest coloured bar, and then the lines are showing you the cumulative cash flows. So once you've got the model, it's pretty simple to use. So the standalone design premise, I'm assuming, as I said, that most people have seen it, but we got a couple of packs of data like this, which has got, you know, all the things that OGA and OGTC wanted to model. They provided us with these two cluster scenarios to evaluate and determine whether the technology could potentially offer a commercially viable development solution. So there was, of course, recoverable reserves, the production profiles and properties and separations provided. And this was very much a collaborative exercise. This started back in May this year with the first conversations, and there was 5 meetings and many emails and calls in between, and we get quite a lot of input to what we were doing from the guys, which was great. And just to take a quick look at the two clusters, cluster 1 on the left-hand side is basically 2 fields. Field A is 3.6 million barrels and field B is 11.4. There was some complications for us to look at the existing host and the existing drill centre, so we didn't look at that, we just looked at the 2 fields. And then on cluster 2, although there's 5 fields there, once we had done initial analysis on cluster 1, the 3.6 doesn't shape up that well, as you'll see, so we decided to drop the field Q and field S from the cluster 2 analysis. In terms of our assumptions, I'm not going to read through all of these, but we were working with oil at $50 a barrel plus 2% inflation year on year. There's lots of different ways to do that. We didn't use a discount to Brent crude. The production limit of our unit is 10,000 barrels per day. We will be working on a study of the separation process in the near future, and between the separation we can get in the tank and the spar, there's a possibility to increase that, but this is what we've modelled for this case. Gas is used as an energy source, so the separated gas is fueling generators, electricity generators on board that would power ESPs, water injection, tank heating, etc. I mentioned that if there's too much gas, we might end up having to flare, but I know that's a bad word these days, so there's other ways to handle that, and that's one of the outputs from the project that we're working on, is to model for any particular oil and production rate how much gas we'll get, and in a particular scenario how much gas we would consume. Incidentally, if there's not enough gas, we can use crude oil for the engines. We use 330 operational days a year, and chase boat on a 365-day service, but shared in the multi-field example. So where we've got a cluster, one chase boat is chasing the 2 or 3 fields. All drilling and basic subsea costings are included. Cost of capital, we took it 10%. A field-specific feed is included in the costs. Reuse, so in some cases we've used a SeaCaptaur unit on one field until that was drained, and then we've moved it onto another field. In such a case, we've taken the reuse cost to be about 50% of the original capex cost, but I think that could be reduced in the future. I think that's a pessimistic number. NPV, the discount rate was 11.2%, and all calculations are pre-tax and plug and abandon. So, looking at cluster 1 analysis, we, as I mentioned earlier, one field 3.6 million, the other 11.4. We need to do further work to include the existing facility. We considered 5 scenarios. We considered A and B as 2 separate developments, A and B into one SeaCaptaur unit, B then A in series, a stress test on option 2, and the impact of oil price on a standalone field B. So this is what we came out with. In scenario 1, which was A and B standalone, you can see that field A is a very large negative NPV, minus a 151. Field B is better at 52.3, but the cluster is still, of course, negative. So field B with 11.4 generates positive NPV with first use standalone, but field A does not. A and B single unit gives us a decent looking NPV of $103 million. So the combined production generates the highest returns from the scenarios we've looked at here, but field A still has a significant negative NPV. Scenario 3 was B first use, A reuse, and that's also a negative NPV, although the reuse does improve the NPV by 30%. And then the scenario 4, which was the stress test, basically all we did there was we bumped the capex up by 30%, and we put the shuttle costs up by 33%, and that still shows some positive cash flow. The impact on the oil prices is just coming in a minute. And this is the kind of output that we generate here. You've got the graphic, which is showing the dark blue bars are showing you the total cluster revenue, and the light blue line is the cumulative cash flow. So you can see we get to the 103. I would comment on that we used the production schedules that we were asked to use, but when you see the cumulative cash flow, you know, you wouldn't probably carry that on all the way to the end there. You might cut that off about year 5. It's not going to add back much to your NPV, but you get your unit back 2 or 3 years earlier, and it's more pronounced than certain other cases we've looked at. The graphic on the bottom left is showing you the layout of the fields. You get field A at the bottom left with 1 well and a 5k tieback, and field B with 3 wells and also a 5k tieback. And then the key information in the box is just the basic output from the model. So we've got 103 million NPV and a 22% IRR. Cluster 2, as I mentioned earlier, we dropped Q and S because they're so small, and so we focused on the 3, and we looked at 4 scenarios: P, R and T standalone, PT and R in series, P from 1 unit and T plus R from a 2nd unit, and then we stress tested option 3, which was the best. So again, P, R and T standalone, you can see rather large negative NPV. Only field P actually has a positive NPV. PR and T in series was also a relatively large negative NPV, although reuse improved field R's NPV by 34%, and a similar improvement in T, but still not economic. And the best scenario here was 3, with P going into 1 unit and R and T going into another unit, and we end up with a total cluster NPV of 99. So this is the optimal cluster economics in this case, with this facility and the chase boat sharing. Still to consider maybe scaling up the tank and the production. David and I have looked at some cases in that, and it does make quite an improvement if you can get your production rate up from about 10,000 barrels a day to 15. And then we stress tested scenario 3 in the same way as cluster 1 by increasing the capex 30% and the shuttle cost by 33%, and you end up at break even. And here's the graphic for cluster 2. And again, you can see that by the time you get across to about year 4 or 5, you're actually starting to go downhill a little bit on your cumulative cash flow. So you'd probably cut off at year 5 and redeploy your unit to a different field. And bottom left is showing you the layout for this cluster. We've got field P with first use, and that was 3 wells, and then R and T with 2 wells each, and they were 7.5 kilometre tiebacks between them, and an NPV of 99 and IRR of 19%. So in terms of the oil price sensitivity, you can see here that when we started off with field B standalone, it kind of produced NPV about 50 million. But you can see as the oil price goes up, you end up, for some reason, the numbers are not coming up on my slide, but for some reason, I can, on my paper slide here, it's up at $100 a barrel. You're up at 500 million NPV. So field B at 11.6 million recoverable had break even just below 50. But as you can see, even modest increases in the oil price significantly improved the situation. And then the other way we did it was to invert it and say, well, what sort of size field could you go down to if your oil price increases? And you know, you can get down. We think 12 to 15 is the sort of number if oil's at $50 a barrel. But if the oil was ever to go back to $100 a barrel, then you could reduce towards, 4 or 5 million barrels. But it's not all just about the pure economics. There's also field risk involved there. So our conclusions from this are that at the current oil price, the safe, in inverted commas, recoverable reserve from a single field is around 12 to 15 million barrels. It would depend exactly on the configuration of the field. Some of the costs are a little bit field dependent. Reuse of the SeaCaptaur unit, moving it in serial from one field to the next, significantly improves economics. Sharing a common unit has a similar impact. That all depends on the interconnect and tieback costs, and we've had a few varying opinions on that recently. The cluster examples struggle with the late production economics, so we'd probably chop them off. It depends how keen people are to MER. UKS, maybe you keep going till you get the last drop, but who's paying for it would be the question there. A modest rise in the oil price massively improves the economics, and only serial or shared scenarios can withstand a significant capex and opex stress test. We still need to do more work on better defining the non-SeaCaptaur costs, but that was something that our colleagues for OGA and OGTC were very, very helpful with. And what I was referring to earlier about the tieback costs, we got some kind of updated figures for tieback costs just last week that were not helpful because they were a good bit higher than what I had before, but then we hear about other people that are knocking these costs down further. So there's a bit more work has to be done on that, because if your tieback costs are too high, then it would be forcing you more towards serial development rather than doing it concurrently. And our gas consumption calculation needs some refinement, but we're working on that. I just wanted to finish up by saying where is SeaCaptaur, what's the way forward? We believe our concept is one of a number of opportunities to maximise economic recovery by unlocking small pools and extending the life of old pools. all the components of our system are covered by patent. Patents were originally granted in Australian, but we've got PCT on them, and we're now going through all the individual country filings. We're working on a couple of projects with OGA, or we will be soon, on the process system and hydrodynamic analysis. What we're looking for there is not just to get an answer. We're trying to build design tools that we can use for the next one and the next one after that. I'd already mentioned the design studies and proof of concept by InTech-C, and we are talking to a number of industrial partners about on advancing the system towards first build. So I think SeaCaptaur is a possible solution for the industry in the context we're talking about here in the 30th round in relation to the unsanctioned field study released by OGA last year. This cluster study clearly shows the benefit of serialisation and a multi-field solution. New collaborative ventures involving several fields and or owners would appear to be the best way to maximise economic recovery. And I pose the question, and we might come to it in the panel discussion, are we ready for this in the UKCS? Finally, I would like to say, if anyone would like their field modelled, please come and ask us, and we'd be happy to do it. Thank you very much.